A person starts at rest at r equals infinity and falls radially towards a black hole of mass capital M. And we want to know how much time it takes on the observer's watch as they move from point r equals 10 gm over c squared to r equals 3 gm over c squared. Then we want to know how much time elapses on the watch of the observer's mother, who is waiting at r equals infinity and just watching it happen. So to do this, there's an observer that's falling into the black hole. How do we describe the observer's motion into the black hole in general relativity? If the black hole is spherically symmetric, we would describe in general relativity, we would use the Schwarzschild metric to describe that black hole's influence on the universe. And in the Schwarzschild metric in general relativity, we have this equation here for orbits, for the movement of bodies influenced by that black hole. In this equation, we set L equal to 0. That's the movement. That's because the movement is radially inward. You might remember that the angular momentum is equal to, it's a vector quantity that is equal to r cross p. And so if your movement is inward into the circle, so you have some circular orbit, and the movement is radially inward, then that means it's towards, so the radius vector is like that, and the momentum vector, the linear momentum vector is also like that. They're both going in the same direction. And what happens to the cross product when the two vectors have an angle of 0 between them? The magnitude of the cross product is equal to the magnitude of each of the vectors times sine of the angle between them. So if the angle is 0, then you have 0 for the angular momentum. And so L equals 0, okay? L equals 0 in this case. And we also get that lowercase e equals 1. The reason for that is because we are told that there is no movement at r equals infinity. That means that the proper time, so tau equals t at r equals infinity. So that means if we substitute r equals infinity into here, we also have to substitute dt by d tau equals 1. And so if we substitute r equals infinity here, we get 1 minus 0. If we substitute dt over d tau equals 1, we get 1. Of course, we can't just substitute r equals infinity. We would really be calculating the limit. So it's like saying the limit as r goes to infinity of e equals 1. But that's okay because e is also a constant. So we know it's supposed to be the same everywhere, including at positive infinity. So we're just going to set e to equal 1. And that means here we have e squared minus 1. That's going to equal 0. 1 minus 1 is 0. So we have the right side is 0. We have L squared, L over CR squared, that's also 0. So we end up with this equation here. And we see this, when L equals 0, we have 1 minus 2gm c squared over r times 1 plus 0 minus 1. So this just ends up being, times 1 plus 0, which is just 1. So we have 1 minus 2gm over c squared r times 1, because this is 0, so we have 1. So we just have 1 minus 2gm over c squared r, and then we subtract 1, because we have a minus 1 outside of the brackets. So then this plus 1 cancels out with that minus 1, this c squared cancels out with this c squared, this 2 cancels out with that 2. We have just that this left side equals 0. We can square root both sides. In the end, we have dr by d tau equals this expression here. And then we can rearrange to get d tau in terms of dr, and we get this expression here. Here we're just multiplying both sides by d tau, and then dividing both sides by dr. So we multiply d tau on both sides, and then we're dividing both sides by this 2gm over r. So I could have said 2gm over r to the negative half, but instead I'm just saying r over 2gm to the positive half. I've circled this in purple because that's going to be useful for the next part of the question. For now, let me just get through this one time, and then we'll get through everything in more detail after. So now we're going to integrate from the first position to the second position. So r of A and r of B, and the proper time at A and the proper time at B. So we're going to integrate both sides of this equation from A to B. On the left side, we have the integral of d tau. On the right side, we have the integral of d over dr. And we have that r of A equals 10 gm over c squared, and r of b equals 3 gm over c squared. That was given in the question. So now we're just doing a simple integral. The integral of 1 is just, the integral of 1 over d tau is just tau. So we have tau at b minus tau at A, and that, we'll just call that delta tau. That's the amount of time that elapses as this movement, as the observer moves from position A to position B. Then on the right side, we're just doing this integral that they gave us. We can go through it in more detail afterwards, but basically we have the integral of r to the half dr. The integral of r to the half is 2 over 3 r to the 3 halves. And so then we evaluate this at r of b and r of a. And so we sub in the r of b and the r of a. We end up with this expression here, root 2 over 9 times gm over c cubed times 10 to the 3 halves minus 3 to the 3 halves. And just to make sure the units are all making sense here, because I'm getting a time, I should have something in units of seconds. The units of g, they're meters cubed per kilogram per second squared. Units of m, that's kilograms. So the kilogram inverse cancels out with kilograms. At the bottom, we have speed of light cubed, that's meters cubed per second cubed. So meters cubed second to the minus 3. And everything cancels out except you have s to the minus 2 over s to the minus 3. That ends up being just seconds in the end. We have a minus 3 at the bottom. That ends up being a positive 3 at the top. A minus 2 at the top becomes a minus 2 at the bottom. So we have 3 minus 2 is equal to 1. We have only seconds to the power 1, which is what we want for the time elapsed for the travel. The second part of the question, we're now thinking about the observer's mother watching this person falling into the black hole. So now we're interested in how much time is observed on her watch. And on her watch, it's going to be, we're dealing with t instead of tau, the mother's time instead of the proper time of the observer. So now we're using this equation. And once again, we were told that it was radially inward motion. So d theta and d phi are both going to be equal to 0. D theta, the angle theta and the angle phi, they're both constants as this motion happens. So we have this equation here. And if we make the substitution, we're seeing this, we're seeing 2gm, we're seeing r over 2gm, or c squared r over 2gm, what we have here. We're seeing that very often. That's coming up over and over again. So let's just make that equal to x. So then we have just x times dr squared equals this over here. We can rearrange this because we want to do the same as what we did last time. We want to integrate over dt. Instead of d tau, we're going to integrate over dt. Another thing I've done here is I've substituted for d tau, I just plugged in that what I had circled in pink before. So I had circled in pink this d tau as a function of dr. That's circled in pink over here, d tau as a function of dr. So d tau in terms of dr, we're going to plug that in to the d tau in this equation. So now we have only, so this d tau is now, I'm plugging in the expression for d tau in terms of dr. So now I have just dr and dt. And so then I'm doing the same thing as what I did before. I'm going to integrate with respect to dt and integrate with respect to dr. So here I have, I'm going to rearrange everything so that I have dt in terms of dr. And here I have dt squared equals something times dr squared. I have some complicated expression here, x plus 1 minus inverse of x to the negative 1 divided by c squared times 1 minus x. So x plus 1 minus x to the negative 1 all to the negative 1 divided by c squared times 1 minus x to the negative 1. That's a bit of a complicated expression. So I'm just going to use wolfram-alpha's simplify function to get a more simplified version of this. You could just calculate this yourself. It's like grade 9 level math, but it's complicated. So we end up with x cubed over x minus 1 squared. and this is times c squared at the bottom. And now we had dt squared and dr squared. So let's square root everything. We get dt equals 1 over c times x to the 3/2 over x minus 1 dr. And I've once again, I've done a variable substitution, x equals that thing I wrote above. So because I did that, I also have to transform the dr, the integration variable. So with this transformation, dx equals c squared over 2gm dr, then I substitute dr. I can rearrange this to substitute dr into dx. Then I can integrate with respect to x, where x of b is related to r of b in this way, according to the x equals r, x in terms of r transformation. So then I'm doing the integral of the left side from a to b and the integral of the right side from a to b. And this integral there, it's quite complicated. It's x to the 3/2 over x minus 1. It looks very simple, but when you do the integral, you end up with this, the integral of x to the 3/2 over x minus 1. It equals this complicated expression here in terms of an inverse hyperbolic tangent. So 2 over 3 times square root of x times x plus 3 minus 2 times the inverse hyperbolic tangent of square root of x. I know from the book Gravitation by Misner, Thorne, and Wheeler from section 25.5, orbits of particles. We actually have this in terms of a logarithm instead of a hyperbolic arctangent. So we're going to use this formula here. The hyperbolic arctangent of x is equal to half times this logarithm. So if we substitute that into here, we end up with this integral here. So we have the integral of x to the 3/2 over x minus 1 dx. It equals this right there. And then we can plug in xb and xa. So the bounds of the integration we get by the fundamental theorem of calculus. We can calculate this. And then we get that, basically going back to the original question, delta t, the amount of time observed on the mother's clock, is equal to this expression right here, where I've substituted now the expression for x in terms of r. Everywhere where I had an x, I substituted the appropriate value for x in terms of r. So now I have something in terms of r. Then you can substitute rb equals 10 gm over c squared or whatever it was. And then 3 gm over c squared was what it was for the other. Let me get those again. That was 10 gm over c squared, yeah, and 3 gm over c squared. So you can substitute those for rb and ra. And we also know that capital M equals 10 to the 6 solar masses. That's given in the question. So we can also substitute that in, and then we'll get the right answer in the end. So that is the end. If you did want to simplify this logarithm, I've given a wolfram-alpha command for simplifying that. You can also simplify it by hand, but that is one way you could simplify this if you wanted to. So I know I went through that fast. Let's now go through it slower and in more detail.